Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today, lecture 29, related rates. Today we'll talk about a technique in differentiation that's very useful for solving problems involving rates of change. The situation is this. Sometimes in applications, you will know one or more rates of change, and you'll need to find another rate of change. And today we'll discuss a method that accomplishes this. Everything we do today revolves around the interpretation of the derivative as a rate of change. So let's recall that. If f of t is a function of time t, then its derivative f prime of t gives the rate of change of f of t at time t. For example, maybe you have a function p of t that gives the population of a city at time t. And t might be, let's say, the number of years since 2000. So p of t at any time t is a number of people. The derivative p prime of t would be the rate of change of population at time t. And the units here would be people per year. So for example, p prime of 17 might be 3,000 people per year, meaning the population is changing at a rate of 3,000 people per year at time t equals 17. For another example, W of t might represent the amount of water in a tank at time t, and that's number of gallons, say. And you can imagine this tank might maybe being filled up or drained, so the amount of water at time t is continually changing. And W of t tells you the number of gallons in the tank at time t. The derivative W prime of t would be the rate at which water is being added or removed at time t. And this would be in gallons per minute. So for example, W prime of 10.4 might be 75 gallons per minute. So water is being added in at that time at a rate of 74 gallons per minute. So in all of our examples, our functions will represent quantities at time t today, and their derivatives are the corresponding rates of change of those quantities. Let's start with a motivational example, one that is intentionally simple and somewhat artificial so that we can see exactly what ideas are at play and the kinds of problems that we'll be dealing with. Imagine a circle that's growing. The radius of this circle is increasing at a steady rate of 5 inches per second. So as time increases, every second the circle grows by 5 inches, steadily growing. And as it grows, its area is changing. And the question we want to answer is, how quickly is this area changing at the precise instant that r is 10 inches? Now, area is square inches, so the rate of change of area is going to be some number of square inches per second. So we're asking at the precise instant that the radius is 10 inches, how quickly is that area changing? The area of that circle, how quickly is it changing in square inches per second? Looking at this picture, when r is fairly big, as it is here, in 1 second, this circle grows by 5 inches in radius. And the shaded region here indicates the amount by which the area has changed. By contrast, if r were smaller, in 5 inches it grows, in 1 second it grows by 5 inches, and this smaller ring represents the amount by which the area has changed. So you can see in this picture that when r is bigger, the rate of change of area is bigger than it is when r is smaller. So the rate of change of area depends on r, and the question we're asking here is, what is that rate of change of area at the precise instant that r is 10 inches? So to begin a solution, let's give names to the quantities at play. Let's call the area of the circle A, and of course the radius is r. So both A and r change with time, so they are functions of time t. You might think of it this way. Because r changes with time, r is equal to a function f of t, and likewise, a is equal to g of t. Let's think about what we know here. It's given that the radius r increases at a rate of 5 inches per second. So 5 is the rate of change of r, which is f prime of t, or dr dt. So we know in this problem that dr dt is equal to 5. What we're trying to find is the rate of change of area, the rate of change of A. That's given by g prime of t, which you could also write as dA dt. So we want dA dt, and in fact we want it at the precise instant that r is 10 inches. So here we see a rate of change that we know, dr dt, and a rate of change that we want, dA dt. So somehow we want to solve for dA dt from the fact that we know that dr dt is equal to 5. And I'll tell you a procedure that accomplishes this. The first step you want to do is look at the quantities of the rates of change, involved in the rates of change. There's r and there's a. You're going to look for an equation that relates those two quantities. And here you don't have to look far, because for a circle, its area A is equal to pi r squared. That's an equation relating A and r. Now remember, A is really a function of time, and so is r. R is equal to f of t. So when we write A equals pi r squared here, it's really saying g of t equals pi times f of t squared. So both sides of this equation are functions of time. What we can do now to get an equation relating these two rates is to differentiate both sides of this equation implicitly with respect to time t. The two sides are functions of t and they're equal, so the derivatives with respect to t are going to be equal. ddt of A equals ddt of pi r squared. Let's look at those two sides. ddt of A, or remember, A is equal to g of t, so its derivative is g prime of t, or dA dt. So that's just dA dt. And remember, we don't even know that. In fact, that's what we want. We want dA dt. But it looks like we're going to get it in an equation. That's good. So let's look at the other side. We have ddt of pi r squared. Remember that r is a function of time, so ddt of pi r squared is not going to be pi times 2r. You've got to use the generalized power rule here. It's ddt of pi times f of t squared. That derivative will be pi times 2 times f of t times f prime of t, or pi times 2 times the f of t, which is r, times the derivative of f of t, which would be dr dt. So notice that we wanted dA dt, and now we're starting to get it in an equation. dA dt is pi times 2 times r times dr dt. We happen to know what dr dt is. It's 5 inches per second. So we could plug in 5 for dr dt, and we get dA dt equals 10 pi r, square inches per second. Now look at that. Remember we said that the rate of change of area, which is dA dt, would be greater when r is bigger? We now have a formula for dA dt, 10 pi r, and that quantity is bigger when r is bigger. It grows as r grows. So when the radius is r, the rate of change of area is 10 pi r, square inches per second. And what we want is dA dt at the precise instant that r is equal to 10. So to get that, you just plug in 10 for r right here. And you get 100 pi square inches per second. It's approximately 314 square inches per second. So that solves the problem. What happened here is typical for related rates problems. You'll have a situation in which various quantities are changing. You will know one or more rates of change. It'll be given to you. And you want to find another rate of change. Here it was dA dt. The way to proceed is indicated in how we solved this problem. The first thing you want to do is find an equation relating those quantities whose rates of change are involved. In this case, it was the area of a circle. In other problems, it would be other equations. Depends on the problem. You then differentiate both sides of that equation implicitly with respect to t. The rates of change will pop up, and then you solve for the one that you want. To summarize, a related rates problem is a problem where one or more rates of change is known and another needs to be found. To solve a related rates problem, analyze it, draw a diagram if necessary, and next, number 2, and this is important, find the quantity whose rate of change you know. In our motivational example, that was dr dt. And then identify the quantity whose rate of change you need to find. For us, that was dA dt. Next, find an equation relating these quantities. In our example, it was A equals pi r squared. What did we do next? We differentiated both sides of the equation with respect to time t. Or, in some cases, depending on the problem, with respect to the variable that the quantities depend upon. And in most related rates problems, that quantity is going to be time t. And when you do this differentiation, you'll get an equation involving the related rates, or the relevant rates. At that point, you can plug in any constants, and you solve for the unknown rate. This is the procedure that we just used in our motivational problem, and it's the procedure that we'll use in all related rates problems. The details will change and differ depending on the problem, but the basic procedure is always the same. It's the one outlined here, and the one that we just carried out in our motivational example. Let's move on to another example. This example involves a plane that's taxiing down a runway, and that runway is 1 mile from a tower, as indicated here. And it so happens that when the plane is 5/3 of a mile from the tower, the distance between the plane and the tower is increasing at a rate of 100 miles per hour. Now that distance would be here, the distance from the tower to the plane. Let's represent that as y. At the precise instant that the plane is 5/3 of a mile from the tower, when y is equal to 5/3, that distance y between plane and tower is increasing at a rate of 100 miles an hour. The question is to find the plane's velocity at this instant. What is the velocity of the plane as it goes down the runway at the precise instant that the plane is 5/3 of a mile from the tower? That's the problem. So let's think about what's going on here. We'll analyze this. Let's draw a diagram. A bird's eye view of this situation is we have a tower that's 1 mile from a runway, which we'll represent by this vertical side of the triangle. And there's a plane right here, and it's at a distance of y from the tower. So you have a little right triangle. And that plane is taxiing down the runway. As the plane goes down the runway, the quantities y and x change. Those distances change. They increase with t. So this x, it's a function of time. And the distance y between plane and tower, that changes with time t also. So y is equal to g of t. So we have this dynamic picture involved. And let's think about the rates of change that we know and the rate of change that we want to find. We actually happen to know that the rate of change of y, the distance between tower and plane, is increasing at a rate of 100 miles per hour when the plane is 5/3 mile from the tower. So we know that dy dt is 100 miles per hour at the instant we're concerned with. Now, what are we looking for? We're looking for the plane's velocity as it taxis down the runway. And notice that this function x equals f of t, that's a position function for the plane. It tells you how far the plane is from this fixed point at time t. So the derivative of that position function, f prime of t, is the plane's velocity at time t. So f prime of t, or dx dt, that's the velocity of the plane. That's what we're looking for. We want dx dt at the precise instant that y is 5/3, when the plane is 5/3 of a mile from the tower. So at this point, we've identified the rate that we know, dy dt, and we've identified the rate that we want, dx dt. So our next step would be to seek out an equation relating the quantities x and y. Looking at this picture, x and y are sides of a right triangle. X is a leg of this right triangle, and y is the hypotenuse. So we can easily get an equation relating x and y. It's the Pythagorean theorem. The Pythagorean theorem says that x squared plus 1 squared equals y squared. So that's our equation relating these two quantities, x and y. Now remember, x and y are functions of time. So in this equation, you have f of t squared plus 1 equals g of t squared. You have two functions of time on each side, and they're equal to each other. So we can differentiate both sides of this equation with respect to time t. So on the left-hand side, you get ddt of x squared plus 1 squared, or x squared plus 1. And let's think about that. ddt of x squared is really ddt of f of t squared. That would be 2 times the function f of t times f prime of t, 2 times x times f prime of t, or let's write it as 2 times x times dx dt, and then plus the derivative of 1 would just be 0. Equals, on the other side, we have ddt of y squared, and remember, y is g of t, so we have to use the generalized power rule here. We get 2 times g of t times g prime of t, or rather, 2 times y times dy dt. So here we have an equation now relating these two rates, dx dt and dy dt. And remember, we know that dy dt is 100. We know this quantity right here. And we're looking for dx dt. And this is good because we've got dx dt in an equation. We can begin to solve for it. The first thing we can do here is, in this equation, plug in what we know. we know that dy dt is equal to 100 miles an hour, at least 100 miles an hour when y is equal to 5/3, which is the instant that we're interested in. So we'll plug in 100 for dy dt. And here we want to solve for dx dt. And looking at this, we could just divide both sides by 2x to isolate dx dt. Let's do so. On the right, we'd get 2y times 100 divided by 2x, and the 2's cancel, and we get dx dt is 100y over x. Now notice that this dx dt, the rate of change that we're looking for, that we're about to get, it has both a y and an x in it. Y is the distance from plane to the tower. And remember that we want dx dt when y is equal to 5/3. So we can plug in 5/3 for that y there. So good, we get 100 times 5/3 over x. But now what is x? When y is 5/3, we want to find x. Well, we could use the Pythagorean theorem to solve for that. Let's draw a separate little picture here, one that's stationary rather than dynamic. At the precise instant that y is 5/3, we need to find this x. That's this distance. So by the Pythagorean theorem, x squared plus 1 squared equals 5/3 squared. Or rather, x squared equals 25/9 minus 1 when you begin to isolate x. And let's simplify that. That minus 1, get a common denominator here. That's 25 over 9 minus 9 over 9. So x squared is 16/9. So to find our x, we can take the square root of both sides. We'll take the positive of that square root, since x is positive here. And we get x equals 4/3. So when y is 5/3, x is 4/3. That's what we plug in here. And then we simplify, and this turns out to be 4 over 3 reciprocates, multiply times the top. That's 100 times 5 over 4, 125 miles per hour. And that answers our question. At the precise instant that the plane is 5/3 of a mile from the tower, it's moving down the runway at 125 miles an hour. So this is a typical related rates problem. We were given a rate of change, we wanted to find another, we carried out our procedure, and we found that unknown rate of change. Our next example involves a swimming pool, as illustrated here. It's 8 feet deep at the deep end, it's 20 feet wide, it's 40 feet long, and it's 3 feet deep at the shallow end. And this pool is being continually filled with water at a steady rate of 40 cubic feet of water per minute. So as time increases, the amount of water in this pool increases as well, steadily increasing at 40 cubic feet of water each minute. Now, as that happens, the water level, H, at the deep end increases. And if you think about it, the rate of change of H in feet per minute, that's different depending on time, t, and different depending on what H is. When H is really small, when you start out, water is pouring in, and the water level H is increasing really rapidly. But as H gets bigger and bigger and bigger, notice that each minute you've got to fill up more of this volume out here, and it takes longer to affect the same change in H. So you'd expect that the rate of change in H would be slower for bigger values of H. The question that we're going to answer here is this: How fast is the water level h rising at the precise instant that h equals 3 feet? So when h is 3 feet, what is the rate of change in h in feet per minute? That's what we're trying to answer here. So we have a dynamic situation in which the pool is being filled up. The quantity h is changing. The number of feet h increases with time t. We want to find its rate of change at the precise instant that it's 3 feet. So let's analyze this. What's the rate of change that we know, and what's the rate of change that we want? Well, right here, we started out with the rate of change. The pool is being filled at a rate of change of 40 cubic feet of water per minute. So the number of cubic feet of this blue prism here is changing at 40 cubic feet of water per minute. So let's call, that's volume. Let's call the volume of this blue prism of water V. V is the volume. So we know that dV dt is 40 cubic feet per minute. That's what's given to us here. And what do we want to find? Look for the question mark. How fast is the water level h rising when h is 3 feet? So we're looking for the rate of change of h, and that would be dh dt. So we want dh dt when h equals 3 feet. So now we've identified the rate of change we know and the rate of change we want. And looking at this, you can see that those rates of change involve volume V and height at h. So our next step in our program for solving this problem would be to find an equation relating V and h. We need an equation relating this V, the volume of this prism of water, to the height h. To figure out that equation, we'll do it over here. We'll sort of pause at this point. We'll find out that equation here, and then we'll write it there and continue the problem going down that way. So to work out an equation relating V and h, let's pull this prism out and analyze it. It's h feet high, it's 20 feet wide, and you've got that volume, that's the volume of the prism. And we want to find an equation relating the volume V to the height h. Now think about what that would be. V is the volume of a prism, a triangular prism. That would be equal to the area of the triangular base, this triangle here, of height h, times 20. So V is the area of this blue triangle right here, times 20. That's base of the prism times the height of the prism. So good. Now we need to find the area of this triangle. Now a triangle has an area of base times height, and here the height is h, and its base would be this length. Let's call that z. And notice that z changes with h. As h increases, this horizontal part of the prism, z, changes as well. And the area of this triangle would be 1/2 base h, or base z, times height h. So v is 1/2 z times h times 20. So this is beginning to get an equation relating v and h. But the thing is, we also have this quantity z in there. We got 3 variables, v, z, and h. What we need to do here is express z in terms of h, so it's just v's and h's in this equation. And then we're good. We can go back to here. So how are we going to figure out what z is? For this, think about the side view of this swimming pool that I've drawn here. And we see this blue triangle of height h and base z in its side view. And think about similar triangles. I'm going to draw a dashed line from the shallow end of this pool all the way across. So the distance between the deep end of the pool and this dashed line would then be 5 feet, because remember, the total depth of the pool on the deep end was 8 feet. So subtracting 3 feet from 8 feet gives you 5 feet here. And notice you have similar triangles. This little blue triangle is similar to this triangle with a dashed horizontal side and a height of 5. So we can use similar triangles to relate h and z. By similar triangles, z is to h as 40 is to 5. Z over h equals 40 over 5, and 40 over 5 is 8. So we get an equation relating z and h. Z over h is equal to 8. Multiply both sides by h, and we get z equals 8h. So there we go. This z here, it changes with h. It's always equal to 8 times what h is. So this z equals 8 times h. And now we can go back up here to our prism. Its volume was 1/2 z times h times 20. And we just figured out that z is 8 times h. So we plug in 8h for z. V is 1/2 8 times h times 20. And that gives us an equation, v equals 80h squared. So this is our equation that we needed here, relating v and h. V equals 80h squared. So having done all of this work off to the side, let's go back here. We've got our equation. Remember here that v and h, the quantities in this equation, they're functions of time because they depend on time. As t increases, that volume is increasing and h is increasing too. So we have one function of time, v, equals another function of time, 80h squared. So we can differentiate both sides of this equation implicitly with respect to t. Let's see, ddt of the volume, that's just dv dt, the derivative of v with respect to t. And what about the other side? It's ddt of 80 times h squared. That's not going to be 80 times 2h, remember, because h is a function of t. We have to use the generalized power rule here. It's 80 times 2 times h to the power of 1 times the derivative of h, which is dh dt. And that gives us 160h times dh dt. So at this point, we have an equation relating these two rates of change, the one that we knew to the one that we want. At this point, we can plug in what we know. We know that dv dt is 40 cubic feet per minute. That was given to us. So put in the 40 there. We get 40 equals 160h times dh dt. And remember, we're looking for dh dt. We can solve for it by dividing both sides of this equation by 160h. So dh dt equals 40 over 160h. Simplifying, that's 1 over 4h. So dh dt, the rate of change of height with respect to time, is 1 over 4h feet per minute. That tells us the rate of change of height for any h, and that depends on h. And remember how we said it looks like the rate of change of h would be smaller when h is big? That's exactly what's happening here. The bigger and bigger h is, the smaller and smaller this fraction, 1 over 4h is. So that meets our expectations. dH/dt depends on the height h. Now we're looking for dH/dt at the precise instant that h is 3 feet. So all we have to do to find our answer is to plug in h equals 3 to this expression for dH/dt. And we get 1 over 4 times 3, or 1/12 feet per minute. And that answers our question. At the precise instant that the depth of this pool is 3 feet on the deep end, that depth is changing, increasing at a rate of 1/12 feet per minute. That's 1 inch per minute. You can almost see it rising. 40 cubic feet of water is being poured into this pool. When h is 3, that water level is rising at 1 inch per minute. So there we go. We've solved this problem. And you can see that often in related rates problems, you have to do a lot of side work to figure things out. All of these problems will be different. The details will differ. The thing that's common to them is the technique. To summarize, a related rates problem is a problem where one or more rates of change is known and another needs to be found. To solve a related rates problem, you do what we did in all of the problems today. You analyze it, you draw a diagram if you have to. Then identify the quantity whose rate you know, identify the quantity whose rate you need to find. Then you find an equation relating these quantities. Next, you differentiate both sides of the equation with respect to time t, or with respect to the variable that the quantities depend upon, usually it's time t, and you'll get an equation involving the relevant rates. At this point, you plug in any constants, and sometimes you'll have to solve for these constants using whatever techniques apply, and you saw that happening today. And finally, in the last step, you solve for the unknown rate. So it's important to work lots of examples of this. You'll get good at it quickly. A couple of pitfalls that I want to talk about briefly is, and I see this happening a lot of times when students first start off with rates of change, sometimes there can be a temptation to carry out step 5 too quickly. If you plug in the constants before you differentiate both sides, you'll get an equation relating to constants, and then you differentiate and you get 0 equals 0. And there's really nothing wrong about that. 0 does equal 0. It just doesn't answer the question. And the thing is, you plug those constants in too quickly. When you differentiated, everything disappeared. You want to wait and plug in your constants at the end, so when you differentiate, you're not differentiating constant functions. So watch out for that. So as I said, get some practice with these. And this concludes today's lecture. And it also completes part 3 of the course on derivatives. We've come a long way. In our next lecture, we're going to start part 4 of the course, where we talk about applications of differentiation. At this point, we know how to find derivatives. We have a bunch of techniques. We're going to begin to apply them in the 4th part of the course. I'll see you then. Goodbye.